Welcome back to Cloud 42, I'm James. Last week we looked at the design for a diamond grinder made using an old lathe motor and some diamond lapping plates. This week we're going to get started on the build, starting with the electronics enclosure. Okay, the first thing we need to do to mount the electronics on this motor is to make this spacer. The spacer sits underneath the electronics box and on the top of the surface of the motor, and then the screws go through to hold the box on there and to provide a through channel to hook up the wiring to the terminal. Let's take a closer look at this spacer. Now, this spacer can be made out of a lot of materials. I think I'm just going to 3D print it. But I'm going to try to do something a little bit interesting here. This is a grinder, and it's going to be raising a lot of dust, both dust from the wheel, diamond particles, particles of carbide, and I really don't want that stuff getting into the motor, and so I would really like to seal this. The original motor had kind of a flat gasket, and I could get some gasket material and cut something out, but hey, I got a 3D printer, let's try something else here. So what I've done is on this spacer, this is sized to easily contain the terminal, to have the same hole pattern that goes down on the onto the top of the motor, and I put a groove in it to take a gasket. Now we could try to find an O-ring this size, but I think I'm instead going to try to 3D print this with flexible material. So let's take this plastic part, send that over to the 3D printer. Let's go slice it. Okay, I need to lay this down. And I want to do this on the 12-inch. Yeah, 12-inch. And we want that at a PET G. 25% is fine. Let's see what this is going to look like. Okay, the slicing looks fine. We've got a rectilinear fill pattern, and it's going to build up first, then bridge over, but that's a really narrow gap, so I think that is going to be just fine. Okay, let's generate some G-code, send it to the printer. I'm printing the spacer out of PET G. ABS would also work fine here. The only tricky part of this print is that it goes down as two parts at first. The inner part with the screw holes and the outside wall that will eventually enclose the O-ring seal. Until the print gets up to about 3 millimeters off the glass, the parts aren't connected, and we're depending on the outside ring to stick to the glass with just a really small amount of surface area for a 3D print. Once it bridges over, it becomes more stable, unless you're using a material that shrinks like ABS. In that case, the shrinkage after it bridges up high can actually cause the outside part to pull away from the glass, but since this is PET G, we shouldn't have any problems with that. Because of the bridging though, the seal groove on the bottom of the part will actually be slightly shallower than the one on the top. The bridge material sags a little bit, in this case maybe only 1 or 2/10 of a millimeter, but it's enough to be noticeable in the way the O-ring fits. In this case, that doesn't matter at all though, because we're going to 3D print the O-rings, and so we can just adjust the height to get what we want. Okay, so we've got the spacer printed. Let's take a look at the gasket. Now, it would be possible to just get a silicone O-ring in exactly the right size, or more likely design this specifically for a silicone O-ring, but I got 3D printers and flexible filament, so we might as well just go ahead and 3D print one. Let's turn the frame off and take a little closer look at this gasket. And what it is, it has an interesting cross section here, and this is just to facilitate 3D printing. Ultimately, this was 3 millimeters on a side and it was square. In fact, I just used the bottom of the groove as the groove in the frame. I just actually selected this entire bottom and then just extruded it up and made a rectangular section for the gasket. Then I came back, put chamfers on these bottom corners, and then put fillets on the top corners that were exactly half the width of this, so they would make a circle around the top. Now ideally I would have made this entirely round, but printing on a 3D printer, that would mean that on the bottom there would only be a tiny contact patch This is much easier to 3D print if you've got a base on it and then it builds out at a 45-degree angle. So just as a practical matter for 3D printing, this was a much more realistic way to do it. And it'll be much easier to get good, consistent results. Now I want this stuff to be as squishy as possible. If I were to make this solid, this stuff is 85 durometer and it's just not going to have very much squish to it. And so it's probably not going to collapse, or it's going to bend the plastic box under the force of the screws. And so what I'm going to do instead is I'm going to make this thin-walled and hollow. If I were going to make it solid, I might as well just take the 3mm filament, which is just about this size, lay it around the box, maybe even cut it to length and try to melt it together and form an O-ring out of it. But again, it'd be solid and it would be way too stiff. So instead, we're going to try to 3D print this and 3D print it hollow. So let me send this over to Simplify 3D. And of course, we're not going to succeed in printing it that way. So Control L, pick a polygon on the bottom, and that will then lay it flat. Now, I want to print this on my 8-inch printer because that's where I have the Ninja Flex. So we'll select Ninja Flex here, and I am going to take the infill percentage all the way down to 0. We do have this set up with 3 layers on the top and bottom and 2 perimeter shells around the outside. So even though the infill is 0, we should get a fairly solid model. Okay, that's smaller. Let's center and arrange this, and let's slice it. Let's take a look at what it did. Now this should be completely hollow, and it is. Let me zoom in here a little bit closer so you can see exactly what's happening. So the first layer to go down is just going to be some bands around the bottom. Get a second layer on top of that, and a third, and then it should start building up just the walls. 2 filaments thick, and then those around back over the top. Merge together and close. Okay, I think that is exactly what we want. This should be a relatively quick print. Let's save it and send it to the printer. When you're printing with Ninja Flex, you have to print very slowly. This video is sped up significantly. You have to do this because it's so springy and it compresses in the feed channel. Running it very slowly, like maybe 15 millimeters per second, makes it a lot easier to control. It's actually one of my favorite materials to print with, just because of the durability of the finished parts and because of the creative things you can do with it that you wouldn't think you could do with a 3D printer, like printing an O-ring. Okay, now we need to cut out some openings in the box here. And you can see in the bottom, let me go ahead and get a couple things out of the way here. You can see how this thing is going to fit. In fact, I'll even turn the motor off and get that out of the way. So ultimately what's happening is we've got this spacer which is going to be attached to the motor, and we need to make an opening in the bottom of the box to, for the terminals and everything to come through, and the mounting holes. And so to do that, I just threw a sketch on the bottom of the box here and projected these surfaces around the sides of the spacer, and then just cut it out and cut through the box. And so that gives us the geometry that we need to actually mill. And then to mill this, just threw this over into the CAM workspace, create a setup. And in this case, I didn't want to bother reducing everything in the center of this to chips or to get out a drill. So I just selected an 1/8 inch end mill, and so this is just an aluminum specific 3-flute end mill, and did a couple of operations. The first operation is just to bore this out, and then the second operation is an actual contour with a ramp in to just cut the hole. So it just ends up being really simple. We're just going to come down, try to get where I can see this better. It's just going to come down and bore the holes, all 4 of them, because the hole is bigger than the 1/8 inch bit. And then we'll come around, ramp in slowly, and just cut the hole out of the box. And at some point as this is coming around, that piece will just drop out and we'll have our hole in the bottom. Now this whole setup is just, so we're just going to take the whole box and just clamp it up in the mill. We'll have to be really gentle. The lid's on the bottom. You see I've got my coordinate system on this front edge. So we can just take this over, clamp it in the mill, average the two sides, get a 0 on that front edge, get a 0 on the top of the tool, and just cut this out. And we can do exactly the same things with the hole here for the switch. Now for the switch, I actually am going to have enough Y travel to reach both sides of the box, so we'll just center up the coordinate system on the 4 sides of the box, and then use that same 1/8 inch bit and just cut out the rectangle for the switch hole. And again, I got the dimensions for this off of the data sheet for the switch on the manufacturer's website. And then exactly the same thing for the hole in the back side here. In the end for the cable gland for the power cable, and just did exactly the same thing, same 1/8 inch bit, 1/8 inch end mill, and we'll just bore the hole. And at some point, you know, the center section of that will just drop out. Nice and simple. And since I had the geometry anyway from putting together the model, figured I might as well just CNC cut this stuff. Okay. Well, let's go out to the mill and cut some holes in the box. Okay, I got the bud box here and I'm just going to put it in the vise. I had a couple of options for how to do this, and I could have put it in this direction. I wasn't totally sure my Y travel was sufficient, and I could have come out here to the machine and measured it. But I decided it was easier just to put it in this direction because my vise is long enough. So I'm going to just snug this down. This is plastic and this vise will easily crush it. And so I just want to get enough of a grip that it's not going to go anywhere. Again, the machining forces are going to be very, very light. First thing I'm going to do is cut the opening in the bottom. And so I need to 0 up on the edges of the box. And for that, I've got an edge finder. Okay, that's the Y with offset. Okay, there I will set my X0. And X divide by 2. And now let's get a Z0. I do have tool 1 selected, which is my edge finder here. And we'll just pull down until we get a good little grip. And again, this isn't going to be super accurate because the plastic flexes, nor does it need to be super accurate because we're milling all the way through. There we go. And we'll set that to the Z10. Okay, 2200 RPM. I am going to use a little bit of air on here just to try to blow the chips free, but there's going to be no coolant. that was easy, and that is a beautiful clean cut. Okay, I'm really happy with that. Next is going to be the switch. Oh, could not be happier with that. That's just gorgeous. Okay, the switch is going to go right here. So I'm going to go ahead and mount this in the vise this direction. And unfortunately, we got to swap tools back because we got to do the edge finder again. As before, beautiful. Might have to thin the box slightly because we are over the maximum thickness dimension for this particular switch according to the data sheet, but it looks like we're going to be fine. Actually, yeah, we're going to have to thin this at the bottom just a bit. Though it may not matter because all the force is going to be pushing in. Yeah, that looks good. Okay, the last hole is going to be in the end of the box for the cable entry, and that will be up here on the top. And as before, that is just beautiful. Well, let's take this over to the bench and put it all together. Okay, we've got all the parts that we need now, and all we have to do is assemble it on the motor. This is the spacer. Now, the spacer that you saw me make was 15 millimeters thick, and after doing a little bit of testing with that, I realized that when the box sits on this, it was going to hit this screw on the top of the motor. So I extended another 5 millimeters. This is now 20 millimeters thick. 3D printed with the grooves, and I have 2 of the O-rings that we 3D printed, and just have to seat these into the grooves. Just going to start with the corners. Try to get these in without twisting them, and then seat those down. And if you can see that, it's sticking up just a fraction of a millimeter, 2/10, 3/10, 4/10 of a millimeter. Same thing on this side. Okay, got the gaskets in there. Now this will just sit on the motor and the holes will line up with the motor holes there. And then the box goes on top. And this is the box we milled out. I know it's all black, so it's hard to see. So we've got an opening that's got the right screw holes in it to fit over that. And that should just sit right down on top. Okay, grab some screws. Okay, so we've got the box on there, we've got access to the terminals. Let's go ahead and put in the power cord next, just because the ground wire is going to be all the way at the bottom. Okay, and then I'm going to bring the ground wire around here. I don't recommend dropping the washers down here in the bottom of the enclosure. Okay, so I've got one of these shake-proof serrated washers. Make sure we get good contact on the ground. Okay, ground's connected. Now, I don't have the wiring diagram here, but we're going to put the jumpers across these two, and the capacitors go around the end. So these are the capacitors, and to fit these in here, let me just go ahead and connect these first. The white wire is for the larger of the capacitors. Then the center wire between the two capacitors is gray. It goes here. Then the blue wire for the other side of the run capacitor. And the first of our jumpers, because we have to jumper these two terminals together. Okay, now I think I'm going to make the bottom ones here the hot side, and so that's going to go through the switch. So I'm going to feed this in. I've got a black wire here that's going to be coming from the switch. And then the white wire, which is the neutral, is going to be coming in over here on the other side, well, along with the second jumper. Sorry, my big hands are in the way here. And then the last thing that we need to do is, because the switch is illuminated, we need a neutral wire coming over to the switch as well. And so I'm going to take that off of this second terminal, which is also jumpered to the neutral. And that's ultimately why I decided to put the neutral on this side, is because then we won't have more than 2 wires on any one terminal. Okay, so we've got the black wire coming in from the power that will connect through the switch to this black wire, which goes down and feeds these 2 terminals, which are paralleled. Then we have the run capacitor across here and the start capacitor across here. Of course, those are just hanging outside right now. The neutral wire is this white one, comes in, goes under, and connects to this side, and is jumpered across, and then we have a spare neutral wire here to go to the switch. Now, let's talk a little bit about this switch that we're going to use. This is an illuminated switch, and there's a couple of different ways you can wire this up. This is essentially what's happening. Let me find something I can point with. This inside the dotted rectangle is the switch itself, and it has 3 pins, 1, 2, and 3. Between pins 1 and 2 is the actual switch that opens and closes when you tilt the rocker, and between pins 2 and 3 is the lamp. And so there's 2 ways you can hook this up. The way I've shown it here, if the hot wire comes into pin 1, no current flows anywhere while the switch is open. Then when the switch is closed, the hot, if you have the motor on pin 2, then the hot goes down to the motor, which is connected across to the neutral, and the motor runs. And some current also flows through the lamp down to the neutral, so the lamp comes on when the switch is on, when the motor's running. When the switch is off, the light in the switch is not on. However, if you swap pins 1 and 2, then you get a situation like this where the hot is connected to pin 2. There's no path over to the motor, so the motor doesn't run when the switch is off, but the lamp does. So you always have current flowing from the hot through the lamp down to the neutral. So the lamp is always on, whether the switch is on or not. And then when you close this switch, the hot can flow to the motor, turning the motor on. And so you'd use this if you want the switch illuminated so that you can find it, in the dark. And you'd want to do it this way if you want the switch to actually show, the light lamp to actually show whether the switch is on. This is the one that I'm going to use, so I'm going to hook the hot wire to pin 1. So this is the hot wire. I'm going to run it through the opening here so we can see what's going on. And that will hook to pin 1 of the switch. Then pin 2 needs to go out to the motor, and that's this line. Put that on pin 2. And then this is the neutral, and I'm just going to run it through the hole here and put it on pin 3. Maybe, if I can get this on. Okay, so that's our switch wired up, and then it should just snap right into the hole that we machined. And it does. Sorry about the video, I've just lost a camera. My third camera is just shutting down. It is very warm out here in the shop, and I don't know exactly what's going on, but it's just turned itself off, and I can't get it to come back on. It's very hot to the touch. Last thing I need to do is to put these capacitors into the box. Now I could just stuff them in there, fold everything up, put the lid on it, and we should be good to go. But I don't want to do that. These were originally in the back of the lathe, and the lathe is like 400 pounds of cast iron, so there wasn't a huge amount of vibration, but still they're a little bit scuffed up from what vibration there was. There's going to be a lot more vibration in this box because we're sitting right up here on top of the motor. And I don't want any damage to the capacitors. I don't want them to, wear against screws in here and eventually abrade through and cause a problem. So I want to soft mount these. So this is the solution that I came up with. These are 3D printed parts made from NinjaFlex. So these are, completely flexible. And what this is just a plate on the back with a little bit of a rim around the outsides, like a millimeter, 1.4 millimeters thick, I think. Just enough to kind of create some soft bumpers around them, and then 2 rings that fit around the capacitors. And to size these, I just measured the capacitors with a caliper and then drew these up in Fusion 360 so that the inside diameter is 1/4 of a millimeter smaller than the diameter of the capacitor, and that should make it so that they will just fit on securely and hold the capacitor. Now these are actually 2 different sizes, so I put that the wrong way first. So I've got one that'll go on this end so that this will just fit up against the side in here and kind of tuck into the corner, and one to go on this end. But I realized after I made these that they won't go over because of the wires, and not just because I hooked it up, but because these 2 capacitors are connected together. Fortunately, NinjaFlex is very flexible, hence the name, so I can actually just stretch it over the capacitor and it will go through, and then I can put it on from the other end. Same thing here. Elongation of this stuff is supposed to be 300%, but I've, never done that. Okay. That's through on that side and that side, and I'm just going to turn these so that the markings are up, just to make it easier for people in the future. And then snap this on the other end, and there we have 2 soft mounted capacitors. And those will just go right in here. Yep, and they don't go anywhere. They're not touching anything. They're not moving. And that should be perfect. Now let me tuck all the wires down here. And we should be able to button this up. Lid goes on the top. Believe in living life dangerously, so we'll go ahead and put all these in. And that is the package. So we've got the box on the top of the motor with the spacer, got the O-ring seals in there, and we have a switch. And the cable gland is protected on the other end. Only thing left to do is try it. Switch is off. Going to plug it in. And while I'm thinking about it, and before I throw the switch, safety glasses, just in case something goes bang. Plug into power, and with any luck, when I flip the switch, we have a motor. Nice and simple. I did not check the illumination. Let's turn this on its side so you can see that as well. And no illumination from the switch. I'll have to dig into that and see if I can figure it out. This is a secondhand switch that I took out of an old plug strip, so it's entirely possible that it just doesn't work because it doesn't work. Well, that is the motor electronics complete, and I am very happy with that installation. I'm happy with how it looks. I'm happy with how it works. And now that we've got that taken care of and we've got a motor that spins, we can turn our attention to attaching a lapping plate onto the front of this and building a tool rest and all the other things that we need to do, and we will continue working on this next time. If you're enjoying these videos, please give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.